topics. Number one, performance. Number one, performance. Some important issues from the performance, then cache memory. Some important topic from cache memory, then instruction pipeline. So this is the first one, second one, and this is the third one. So we'll cover all these topics, the selective topic from these portions. We already take the classes on these topics. So again I am showing you in board clearly, and you minutely follow these classes and note down all these things. Okay. So from the performance we will see what is called the clock cycle time. So at first, from the performance, we will see clock cycle time. Clock cycle time. Are you hearing me? Any problem? Hello? Are you hearing me? Any problem? Okay, all fine? Okay. Clock cycle time. I already teach you all these topics, but I don't know whether you prepared all these topics or not, I don't know. So follow this class minutely, and you have to write the questions from all these topics. Clear? So these are the very, very easy topic, no problem. You can write all the questions if you can hear the class clearly. Okay. So clock cycle time. So what do you mean by clock cycle time? Short form of clock cycle time is CCT. The short form of clock cycle time is CCT. Clock cycle time. Clock cycle time means within every processor there is a clock. In every processor there is a clock. Okay. So the clock. So this is and clock. So here clock cycle time means the duration of that clock is called the clock cycle time. So this is the duration of clock cycle. So CCT, this is the CCT. So clock cycle time. So this clock cycle time is very, very important terminology for calculating the different performance of the computer system. So in the chapter of performance, the clock cycle time, understanding the clock cycle time is very important. Then clock rate. So if you understand the clock cycle time, that's mean a clock. The time for a clock pulse. The time for a clock pulse of the processor is called the clock cycle time. Clear? Then if we understand the clock cycle time, then we will clock rate. What is called the clock rate? Clock rate. So clock rate is mentioned as hertz. The unit of clock rate is hertz. So clock rate will be 1 by CCT. This is the clock rate, and its unit will be hertz or kilohertz like that. Okay. So number one thing is clock cycle time. Number two is clock rate. These two terminology is very important. Clear? So from the performance we are learning some terminology. So this is the first terminology. First terminology is clock cycle rate. Second terminology is clock rate, and third terminology is throughput. Now we'll see what is called the throughput. So throughput. So let's see what is called the throughput. So very simple questions. I will give you very simple questions. All of you have to write all these questions and you have to submit that on Google Classroom. So clear? So then throughput. So what do you mean by the throughput? Throughput means number of instruction executed per second. Throughput means number of instruction executed in per second. So instruction per second. So throughput will be instruction per second. This is a throughput. Clear? So number of instruction per second. So the throughput of different processor will be the different. So the performance of the processor can be analyzed by this throughput. So these three terminology from the performance, and using this terminology we can solve different numerical method. And already you have a video. Already I have a video on this particular topic, performance, in YouTube channel. You can follow that video, and within that video some problems also solved on that video. So again you can see that video and you can prepare all this topic, all these things. But today follow all these things clearly, then I will give you questions from only from these topics. Clear? So this is the some important terminology that we should know from the performance chapter. Next we will go to the cache memory. Some important issues about the cache memory. So at first we have to know what is the cache memory. We don't know cache memory is what. Cache memory is the memory, faster memory, that is placed in between the CPU and the primary memory. So within the CPU and primary memory, a faster memory is placed, that is called the cache memory. So from the cache memory we have to learn some important terminology. That one important terminology. So there are so many important terminology we should know from the cache memory. So one of them important terminology are cache hit and cache miss. Then page, though the page hit and page miss, these are not related with the cache memory, but you should know the definition of these two terminology in this context. So page hit and page miss. So what does it call? So suppose this is your CPU. Suppose this is CPU and this is your cache memory, and suppose this is your main memory. This is your main memory. Clear? So when CPU request for particular word, when CPU request for particular word from the cache memory. So when CPU requests some word from the cache, if that word is present within the cache, then that is called the cache hit. That is called the cache hit. Okay. Now, if the word is not present in the cache memory, then that is called the cache miss. Clear? So this is the cache hit and cache miss. These two these two terminology is very, very important for performing the different mathematical solution from the cache memory. So these two terminology is very, very important to understanding perspective. What is called the cache hit and what is called the cache miss. Clear? Next page hit. What do you mean by page hit? So suppose CPU access some request some word from the cache. If that word is not present in the cache memory, then it will be searched in the main memory. It will be searched in the main memory. If that particular word is not present in the main memory also, then that is called the page miss. Okay. If that word also not present in the main memory, then it is called the page miss. And if that word is present in the main memory, then that is called the page hit. Page hit. Because if that word is not present in the main memory, that means that word will be present in the auxiliary memory. That means there is a concept of the virtual memory comes in that particular position. Virtual memory concept comes here. So that is called the cache miss, page miss and page hit. So these are four important terminology associated with the cache memory. Clear? Next we have to know other two important terminology related to the cache memory. That is the locality of reference. Locality of reference. This is very, very important terminology. Locality of reference. Locality of reference. All are conceptual things I am showing you. All the important conceptual things I am showing you, and I also give you the questions from all this topic. Clear? So okay. So locality of reference. locality of reference. Locality of reference. Locality of reference are two types. Locality of reference are two types. One is called spatial locality and another is called temporal locality. So locality of reference are two types. Number one locality of reference, that is called the spatial locality. Spatial locality, and number two is called the temporal locality. I will suggest you take the notes simultaneously. If you take the notes simultaneously, then I think your note will be prepared. Clear? As I am doing that's why I am doing the board work. Board work is the best way of teaching, because students get times to write down something in their notebook. So spatial locality and temporal locality. So what is called the spatial locality? Spatial locality means when CPU access a word from the cache memory, then what happens? In the next time, there is a high probability of accessing the words surrounding that words. That means nearby words. That means suppose this is your memory location for cache. Suppose this time the CPU is accessing this particular word. So in the next time, there is a high probability of requesting the words that will be neighbor of this particular word. That means surrounding words. There is a high chance of requesting the surrounding words. That is called the spatial locality. Okay. So spatial locality you can write down next time. হ্যাঁ লিখে দিচ্ছি, ঠিক আছে? Next time we will request next time we will refer a word around the previous word. That means suppose for this particular instance of time you are accessing some word. In the next time there is a high probability of accessing the words, their surrounding words. That's mean nearby words. Got it? So this is the spatial locality. This is called the spatial locality. This is a very important terminology associated with the cache memory, because cache memory concept comes from these two particular concept. So from the concept of the locality of reference is very, very common question in computer architecture. So this is very important concept. So because of this locality of reference, the cache memory concept comes. Otherwise, there is no logic of using the cache memory. This is the logic why we should use the cache memory in between the CPU and our primary memory. Then temporal locality. So temporal locality, you can write, we need a recently referred word referred word. Is it visible? Everything is visible in the board? Okay. So we need a we need a recently referred word in near future. Near future. That's mean suppose this particular time you are accessing a word. So in the near future, there is a high chance of accessing that very word. Why? Because if you study the characteristics of the program, features of the program, then you will see most of the program have the loop type structure. So loop type structure means what? The same structure, same statement will be executed again and again. That's mean if you refer a particular word in the next time, that's mean within a loop, after some time, there is a high chance that particular word will be accessed. That is called the temporal locality. So these are two very important concepts: temporal locality and spatial locality. These are called the locality of reference. Clear? So from the cache memory, we have this important terminology. Now from the cache memory, we have to know other two important terminology that is associated with the write policy of the cache memory. So what are the different write policy of cache memory? So read policy and write policy. Write policy means when you write something in the cache memory, then what are the different policy? There are very two important policy for the write policy. So they are called the write back and write through policy. So already we have the videos on this particular topic also. So that's why I told you. So we covered so many topics in the video, and you can answer a lot of questions from those videos also. So okay, so video is video, but this face-to-face mode is more important. So cache write policy. So cache write policy. So there are two write policy. One is called the write through. Write through policy, and this is number one, and number two, write back. Write back. So there are two important write policy of the cache memory. One is write through and another is write back. Write through and write back. So what is the write through and write back? Suppose this is your CPU. Suppose this is your CPU. Suppose this is your cache memory. So this is your cache memory. Okay. So and this is your main memory. Suppose this is your main memory. This is your main memory. So now what will happen? This is the write policies. You have to know this is the write policy, not the read policy. How the data will be read, that's not the policy, it's the write policy. So now what happens? The block, the particular block or word that present in the cache memory, obviously that word also will be placed in the main memory, because all the data comes from the main memory. So when the machine will be power off, there will be no data in the primary memory, but when you boot the machine, the instruction that will be executed that in the CPU, that will be present in the main memory. Then from the main memory it comes in the cache memory, and from the cache memory it comes in the CPU register. Clear? So now suppose a particular word is present in the cache memory. Obviously that was also present in the main memory. That word also present in the main memory. Now when the CPU writes some word in the cache memory. Suppose CPU will write some word in the cache memory. CPU will write something. Write something means suppose there is an value a equals to 5. Suppose there is a value a equals to 5. A equals to 5. Now you update it. Now it's become a equals to 7 or something else. Got it? So when you write something in the cache memory, so that particular copy also present in the main memory. So that copy also should be modified. So how we modify that things? we can modify in two different ways. One way is that when you modify or write something in the cache memory, cache block, a particular word in the cache block, then at the same time you also update that word from the main memory also. When you update something in the cache memory, at the same time you also update that things in the main memory also. Clear? So that is called the write-through policy. That is called the write-through policy. Write-through policy. This is so simply. I will ask you very simple questions. So just remember all this terminology: write-through and write-back. So what is write-through? So when CPU will write something in the cache block, at the same time that particular word also will be updated in the main memory also. So at a time it will be updated in cache and main memory simultaneously. Clear? That is called the write-through policy. But we can take the another approach. Another approach is what? Suppose now A becomes 7. In the next time A may be updated in 8 or any other values also. So it may be updated multiple times. So suppose at first it was A equals to 5. Now it becomes 8 equals to 6. Next time it may be 8 equals to 9. So every time if you choose the write-through policy, then every time you have to update the word in the main memory also. But it may happen that when you update some memory in the cache memory, then when you replace that block in the main memory, in some time you have to replace it, because it is a cache mapping. Cache mapping, because we know that using the cache mapping we will replace the block from the cache memory to main memory. So any block present in the cache memory must have to replace. After some time it have to replace, because main memory size is large. All the thing cannot be present in the cache memory at a time. So the total number of word or memory that is present in the main memory at a time, all the word cannot be present in the cache memory because its size is very small. So what to do? You have to shift these blocks from the cache to main memory. That is called the mapping techniques. There are different mapping techniques. I also teach you what is called the different mapping techniques: direct mapping techniques, associative, set associative. All these are the different mapping techniques. So whatever the mapping technique is used, ultimately your block will be replaced in the main memory. After some time your block will be replaced in the main memory. Got it? So when you replace it, only then you will update that. So you can update this word can be updated multiple times, but at a time, after some time, once it will be replaced in the main memory, but then at the final time it will be updated in the main memory. Every time you need not update the word, when you have to update in the cache memory. If you follow this particular protocol, that protocol is the write-back protocol. All these things also called the protocol also. This is called the write-through protocol and write-back protocol. All these are the protocols in the cache memory mapping. Clear? So these are some important terminology from the cache memory. Now we will see our next topic, that is the instruction pipelining. Instruction pipelining. Clear? So now we will see some important terminology used in the instruction pipelining. Our last topic, instruction pipelining. So again I am telling you, I will give you the questions what we are learning today. We have to write some questions from these topics. So you can take the note of this class. It will helps you to write your answer. Okay. So instruction pipeline. Hello. हाँ कर दो अपलोड कर. Okay. So instruction pipeline. Instruction pipeline. Okay. So what is the instruction pipeline? So what is the basic concept? So to understand some important terminology, at first we have to know what is the basic concept of the instruction pipelining. Okay. So instruction pipelining means the total architecture of the instruction handling hardware can be divided into different phases. So what are those phases? They are called the stages. So the instruction can be executed through different stages. So if we divide that instruction execution in 5 different stages, then that is called the 5-stage instruction pipeline. Then it will be called 5-stage instruction pipeline. Clear? So what are those 5 stages? The first stage is called the instruction fetch. The first stage is called the instruction fetch. So instruction fetch, IF, instruction fetch. Instruction fetch. So instruction fetch is IF, instruction fetch, the first stage. Clear? So next stage. So what will be the next stage? Next stage is name is called the instruction decode. Instruction decode, ID. So this full form is instruction decode. Instruction decode. Clear? So the first stage is instruction fetch, second stage is instruction decode, third stage is execution. So the next stage is called execution. So the next stage is called execution. Clear? So then this is the third stage. The fourth stage is called memory access. The fourth stage is memory access. That's mean how a whole instruction is executed, it can be divided into multiple segments. So these are called the segments. So our stage, that's why it is called the whole instruction will be divided into 5 different stages. That's why it is called the 5-stage pipeline. So fourth stage is called memory access. So this is the fourth stage, memory access. And the last stage is called the write back. Last stage is called the write back. The last stage is called the write back. Okay. The last stage is called the write back. So these are the 5 stages. These are the 5 stages of instruction pipeline. So that's why it is called the 5-stage pipeline. So what will happen? So suppose all these are the clock pulse. Suppose these are the clock pulse. First clock pulse, second clock pulse, third clock pulse, fourth clock pulse, fifth clock pulse. Suppose instruction 1 enter into the CPU. So in the first clock pulse, the instruction fetch stage will be executed. Then the second clock pulse, instruction decode will be executed. In the third clock pulse, instruction execution will be executed. In the fourth clock pulse, memory access will be executed. Then and the write back. That's mean all these small stage will require how many time? 1 clock pulse. But if the instruction execute as a stretch, then it required how many clock pulse? 5 clock pulse. So this 5 clock pulse will be divided into 5 different stages. Clear? So this is the instruction 1. Now what will happen if your system is not pipelining system? Suppose your CPU is sequential execution. Sequential execution means your CPU will take one instruction, it will execute the whole instruction, then it will take the next instruction. So if your system is a sequential system, then your second instruction will be accessed by the CPU after how many clock pulse? After how many clock pulse your second instruction will be accessed by the CPU? If your system is the after fifth clock pulse, because first instruction will take fifth clock pulse for your sequential. If you consider your system is sequential execution, not pipelining. Got it? So if it is sequential serial execution or serial execution, then the first instruction will execute, then the second instruction will come, then the instruction fetch of the second instruction will come there. So in the 6 clock pulse, instruction fetch of the second instruction will come, then the instruction decode of second instruction. This way it will take. So this is the serial execution. So if we design our CPU in serial execution, then what will be the problem? Problem will be we require too much, our performance will be very, very low. That's mean throughput. Your throughput will be very low. So now tell me, if you have a serial execution CPU and one instruction required 5 clock pulse, then tell me what will be the throughput? What will be the throughput of that sequential serial execution system? Throughput. What will be the throughput? If you consider the serial execution, then what will be the throughput? What was the definition of throughput? Instruction executed, number of instruction executed per second. Number of instruction executed per second. Suppose you consider all these clock pulse required 1 second. All these clock pulse required 1 second. Now tell me what will be the throughput? Instruction per second. Instruction per second. Okay. Okay. Now instruction per second. So instruction per second means in every, how many instruction will be, that's mean for an instruction how many clock pulse will be required. How many clock pulse will be required? So instruction per second, if you calculate it in instruction per second, then one instruction required 5 seconds. If you consider 1 second, then that by dividing that things you can find out the throughput. That's not the matter. Now I am telling you. So if this is the scenario of the serial execution. Now if we use the pipeline structure, then what will happen? Then for the second instruction, so after first clock pulse, so all these are the hardware components. Actually all these are the hardware components. All these are the different hardware components. Some portions of the hardware perform the instruction fetch, then some hardware portion will do the instruction decode. So in the second instruction, for the second instruction, after first clock pulse, so in the first clock pulse you cannot put the second instruction, because there is only one hardware for instruction fetch. So in the first clock pulse, this particular block is engaged with the instruction 1, but in the second clock pulse this will be free. That's why for the second clock pulse, the instruction in this that means second clock pulse, the instruction fetch operation of the second instruction will execute. So the instruction fetch operation will be done in the second clock pulse for the second instruction. So that way, then the third instruction decode, then instruction execute, then instruction the memory access, then write back. Clear? So that's mean the first instruction, you will get first instruction after 5 clock pulse, but after that in every clock pulse you will get a new instruction executed. So the second instruction, you will get the second instruction in the 6 clock pulse. Got it? It will be executed in the 6 clock pulse. So in the, suppose there is another instruction, third instruction. So that third instruction, the instruction fetch of that instruction will be done in the third clock pulse. Then instruction decode will be in this clock pulse, their execution will be done in this clock pulse, and memory access will be done in this clock pulse, and write back will be done in this clock pulse. So what will happen? Now you can see that something, it is the parallel execution. or concurrent execution. That means all the instructions are executing concurrently, because if you consider the third clock pulse, then in the third clock pulse the first instruction execute is execution fetch, the second instruction executing is instruction decode fetch, and the third instruction executing is instruction fetch phase. So that's mean simultaneously or multiple instruction can execute in the different phase. That's mean you can say it is the parallel processing, or you can say it the concurrent processing. So this way we can perform the concurrent processing. So obviously if you do the concurrent processing, the throughput or speed up will be high, the speed up will be increased. So here previously a instruction you can find out every instruction will be executed after 5 clock pulse. Now you can get a new instruction to be executed in every 1 clock pulse. Got it? That is the benefit. Now we will calculate the speed up. So there is a very important terminology used in the instruction pipeline, that is called the speed up. So actually we have to know that this terminology, speed up terminology. So speed up. The calculation of speed up equals to the time required in non-pipelining system. Time required in the non-pipelining system. So time required in non-pipeline system divided by time required in pipeline system. Clear? So the speed up calculation will be time required in non-pipeline system and time required in pipeline system. Suppose you have n instruction. You have n instruction. To execute the n instruction in the non-pipeline system, how many clock pulse you require? If you have n instruction, if you execute in non-pipeline system, then how many clock pulse you required? Tell me. How many clock pulse you required? In the 5-stage pipeline system, this is a 5-stage, 5n, exactly 5n, because one instruction required 5 clock pulse, so n instruction required 5n. So it will be equals to 5n divided by in the time required in non-pipeline system. Time required in pipeline system. This time is the non-pipeline system and time required for pipeline system. So now tell me, in pipeline system for executing the n instruction, how many time will be required? How many time you required? To execute any instruction in the pipeline system, in the 5-stage pipeline, how many time will be required? C1, no. Suppose after 4 clock pulse, so within this 4 clock pulse, you will not get any instruction to be executed. Clear? So after the 4th clock pulse, you will not get any instruction executed, but from the 5th clock pulse, in the 5th clock pulse, you will get the first instruction to be executed. Then from the 5th clock pulse, in every clock pulse you will get a instruction to be executed. So for the first instruction you required how many time? You required 4 plus you required this 5 unit of time, and the remaining how many instructions remained? n-1. So n-1 remaining instructions are n-1. They required how many time? 1 clock pulse. So the first instruction required 5 unit of clock pulse, and for the n-1 instruction it required only 1 clock pulse. So if we calculate it, it will be 4 plus n. It will be 4 plus n. So to execute 5 instruction in the 5-stage pipeline system, it required 4 plus n unit of time. So here you will write 4 plus n, 4 plus n. Clear? 4 plus n. So now what will be the value? What will be the value from here? So it will be, so it's become the speed up becomes 5n divided by 4 plus n, 4 plus n. Clear? So now see one thing, consider one thing. Suppose you are executing a huge number of instructions. Suppose your n is very high. Your number of n is very high. That's mean your actually your CPU is executing so many billions of instruction, millions of instruction. So obviously n will be a very large number. So if n is a very large number, then 4 will be negligible. So obviously we can write it is 5n by n, because 4n and n will be something equal, because if n is a very large number, then we can neglect 4. So now it will be actually, this will be 5. So the speed up will be 5. So for what type of pipeline system? 5-stage pipeline. What was your pipeline system? 5-stage pipeline. Now if you have 4-stage pipeline, suppose you have 4-stage pipeline, then what will be your speed up? Your speed up will be 4. If it is the 4-stage pipeline, then your speed up will be 4. If it is P stage pipeline, suppose your pipeline is divided into P stage, then your your speed up will be what? What will be the speed up? Yes, P. Anirban Vallabh.